All right, discrete dynamical systems. So what have you learned? What have you learned here in chapter 5? Well, you've learned about how to find eigenvalues and eigenvectors, and you've also learned about diagonalization, where you can take a matrix and express it as P times a diagonal matrix times P inverse, where the diagonal consists of eigenvalues along the diagonal matrix consists of eigenvalues along the diagonal, and the matrix P consists of eigenvectors. So, you've learned a lot of good things, and then we learned about complex eigenvalues too. But okay, it would be nice to see some applications, and a big application is discrete dynamical systems. A big application for eigenvalues and eigenvectors is these discrete dynamical systems. So eigenvalues and eigenvectors provide the key to understanding the long-term behavior or evolution of a dynamical system described by this difference equation. Okay, so x of k plus 1 equals a times x of k. Okay, so such an equation is used to model population movement, and we're going to focus a lot on species here. Animals. Will the animals survive? Will they die out over time? The applications, like they say here, the applications in this section focus on ecological problems because they're easier to state and explain than, say, problems in physics or engineering. And that's fine. We can, you can apply this on your own to physics and engineering. Dynamical systems arise in many scientific fields, and it is really just a truly amazing idea. So let's refresh ourselves here on a little bit of theory that you learned already. So you have eigenvectors, and when you have a matrix A, you find hold on, let me make sure. Yeah, when you have a matrix A, okay, you find eigenvectors and eigenvalues, and so if you have an initial vector that's in, well, I want to say this the right way. So let's say you have a basis, okay, of eigenvectors for an n-dimensional space, R sub n, okay. Well, the eigenvector basis for that Rn dimensional space, there are n eigenvectors in the basis. So any vector in Rn dimensional space, any vector x sub 0, any initial vector, we usually call x sub 0 an initial vector, whether it's initial population distribution or initial population percentages, whatever, any vector x sub 0 can be written as a linear combination of the eigenvectors, because the eigenvectors form a basis for that n-dimensional space. Okay, and it turns out that the eigenvector decomposition determines what's going to happen to the sequence of the x sub k vectors. Okay, the x sub k is information about the system at time k. Okay, so it could give, for instance, the number of well, I want to say this the right way. It could give, let's see here, like the number of, like if you have owls and rats, okay, if the vector x stands, say it's a 2x1 vector, and the two elements in the vector, one number stands for the number of owls you have after k months, and the other element in the vector stands for the number of rats you have after k months. It can stand for the number of animals after k months in terms of the owls and rats in a system. Okay, that's an example. But what we want to do here, of course, is make clear that we can model the evolution of system using the eigenvector and eigenvalue decomposition, okay, where x sub 0 equals that linear combination of eigenvectors. And the reason is because x sub 1 is equal to a times x sub 0, right? Okay, and so that can be written then this way: C1 times AV1 plus C2 times AV2 plus, and so forth, Cn A times Vn. All you're doing is, in equation 1 here, you're just multiplying through the that vector equation by the matrix A. And then, of course, you can factor through the constants. But remember, the vector V's are the vectors V's, the V vectors, sorry, are eigenvectors. And so A times V1 equals lambda 1 times V1. A times V2 equals lambda 2 times V2, and so forth. So x sub 1 is just written the way it is. But then in general, and we actually talked about this. How many remember where I showed you this fact that the x sub k we can get a formula to determine the vector x sub k, and that formula is formula 2. It's a recursion formula, or an iterative formula. How many recall that? Okay, Eleanor recalls that in our discussion. So we already, I already set the groundwork for this particular result, and this result in 2 there is very, very important, because based on that we can let k go to infinity, and we can study how the vector x sub k behaves as k goes to infinity. In other words, what would the evolution of the system be? Okay, and so are there any questions on this? This whole formula that you see here, that second formula 2, where x sub k equals, c1 times lambda 1 to the kth power times the first eigenvector, plus all the way up to the cn times lambda n to the kth power times the nth eigenvector, and the lambdas are the eigenvalues, by the way. That whole formula is derived based on knowledge you learned. Okay, and we're gonna really make use of it. So what I want to do, well, are there any questions so far? Okay, all right. What I want to do is I want to do an example, example 1 in the textbook, but I'd like you to actually have it in your notes. So I'm going to make that example visible. There's going to be a little copying here you have to do, but it's worth it. Let me give you a few moments to copy down this example, okay? And then we'll discuss its solution. Okay, give you a little more time here. Okay. All right. Maybe. All right. Just a little more time here. Okay. Okay. So let's go ahead here and talk about this a little bit. All right. So, all right. What we want to do here is we want to denote owl and rat populations at time k, where k is in months, by the vector x sub k. O sub k is the number of owls in the region studied, and R sub k is the number of rats measured in thousands in the region studied. And what we have here is we have a relationship that helps us determine in the next month. So if K is this month, if we're in the kth month, okay, if the kth month has this number of owls and this number of rats, how many owls and rats would be in the following month, in the K plus first month? Okay, well, we have two equations that guide us here. So the number of owls that are going to be, that we're going to have next month is equal to half times the number of owls this month plus 0.4 times the number of rats that are here this month. And then the number of rats that will be here next month equals negative p times the number of owls that are here this month plus 1.1 times the number of rats that are here this month, R sub k. So I'm just trying to keep it simple rather than use kth month and k plus first month. But you see what I mean. The number of owls and rats that are going to be the number of owls and rats that are present in the k plus first month depends on the number of owls and rats, of course, that are present in the kth month by these two equations. And these two equations they don't just come up with these equations, you know, out of the blue. There is data that is taken, and based on the data, they come up with equations. Okay, how many remember like linear regression models when you have a line of best fit, and the line of best fit is based on a scatter plot based on data, and you know, you get a line of best fit or even a curve of best fit, and based on that, you get equations for a model of best fit. How many maybe you've seen that kind of thing in classes they've had before? The line of, okay, Justin has seen it certainly. Yeah, and so, you know, we always are trying to come up with models to describe science. Okay, and this is an example. So let me just ask you, so let's look at the first equation here. First equation says that the number of owls in the K plus first month equals 0.5 times the number of owls in the kth month plus 0.4 times the number of rats in the kth month. So why would this be positive here? The number in front of the 0.5 in front of the O sub k variable. I mean, and also in front of the number, in front of the R sub k variable, we also have a positive 0.4. So let me ask you, does it, if you have more owls living in the kth month, should that help increase the population of the owls living in the K plus first month? Should we, you know, should there be a, we want to be a little bit careful here. I want to be a little bit careful about this because it isn't like we have a number bigger than 1 there, right? We have a 0.5. So let's see here. And actually, I want to make sure I'm thinking about this in the right way. I mean, all right, let's think of it like this. What does the first equation say? What does the first equation say here? First equation says that, well, all right, let's say that in the kth month, the number of rats were equal to 0. Okay, I mean, this is probably an easier way to think about dissecting these equations. Let's say in the kth month, okay, there are no wood rats, no rats alive. What would happen to the population of the owls? Well, okay, but in 1 month, what's going to happen to the population? Justin says it should decrease. By how much does it decrease? Good, that's right, Benjamin. It halves. Because if you have here, okay, let's think of it. If like, for instance, this month, there are no rats around, that means 0 rats, then that means that the number of owls next month is going to be 1/2 the number of owls this month. And so having no rats, it makes sense that the owl population would decrease. It absolutely makes sense. Okay. Now let's go to this. Well, are there any questions on that? Please let me know if you're uncomfortable. Who's feeling good so far? Who's feeling good so far? Okay, Benjamin's comfortable. All right, well, let's look at the, all right, Elaine's comfortable, Hung's comfortable. All right, well, Very good, very good. Let's look at the second equation. So second equation, let's say that this month, the kth month, let's say that's this month. Let's say that there are no owls alive. No owls in this region, okay? Then that means that next month, the number of rats that will be alive is going to be 1.1 times the number of rats that are alive this month. Does that make sense? Why would that make sense? Why would the rat population grow if there are no owls present? That's right, hon, because owls eat rats. Well, all right, but couldn't the rats though just sort of I mean, why do they have a 1.1 times RK here? Why don't instead they just have a 1 times R sub K? Why do they have a 1.1 here? That's right, Justin. The rats reproduce at a significant rate. They are going to grow. They are going to grow for sure. Okay. All right. And let's look at this another way. So so P is 0.104. Why is so this value here in front of the number of owls in the kth month is negative 0.104. Okay, negative 0.104. So why would that value be negative? Why is this value, this coefficient, why is that negative in front of the owls? I mean, why don't they have this? Why don't they have, hold on here, maybe I can use, this might be good to use my stylus on. Hold on, class. Why don't they have R sub K plus 1 equals positive 0.104 times R, or times OK, plus 1.1 times R sub K. Why do they have a, hold on here, let me just get that O. I mean, what's going on? Why do they have, why not have a positive 0.104? Now wait, there was a chat thing here, hold on. Somebody chatted me something here. Hold on, class. Let me get it. Well, but okay, that the relationship would be different, but I'm wondering why they have a negative value here. Why must that value be negative? Well, let me ask you this. Okay, hung, and that would be that because it decreases the rat's population. That's right. So the more owls there are, okay, the more owls there are, that's going to bring down the rat population, right? So that would mean that the rats, the number of rats alive the following month, are going to be less. Okay, so you have to have a negative coefficient in front of the number of owls. Okay, because the more owls there are, the more the rat population decreases. It has, in other words, owls, think of it like this. Oh, I love this. Owls have a negative effect on the rat population. right? On the other hand, rats have a positive effect on the owl population. How many like that? That kind of thinking, that kind of phrasing. Yeah, yeah. So see, I try to, okay, and that good, good, and that's great. That's great. Well, are there any questions? Are there any questions so far? Okay. Well, what we want to do is we want to determine the evolution of this system. We want to determine the evolution of the system. Okay. How many are feeling good now, feeling better, by the way, with these two equations that model the relationship between the owl and rat populations? How many, with that little discussion, feel better? Okay, Eleanor feels better. Okay, how many feel comfortable before we move on? Because, thank you, Eleanor. Okay, I'm hoping a few more people feel comfortable. Hung does, okay. Andres, wonderful. Okay, I was hoping to get a lot of thumbs up. Maybe, why don't you just, if you're feeling good, just go ahead and give a thumbs up. I'd like to see, kind of like to want to take a class survey. Thank you, Catherine. Thank you, Ariana. Thank you, Natalie. Okay, excellent, excellent, excellent. Okay. Well, all right, now we want to determine the evolution of this system. We want to determine the evolution of the system. So how are we going to determine the evolution of the system? What do we need to find, class? That's right. Good, Benjamin. Eigenvectors and eigenvalues. And of course, in order to find eigenvectors and eigenvalues, based on this relationship between owls and rats, we have to figure out what the matrix A is, right? We have to figure out what's the matrix A. Okay, what's that matrix A? All right, well, so let me see here. One moment, class. Let me just see here. All right, the matrix A is going to be this matrix here. So let me just go back to the original page here. So this system of equations, which models the relationship between the owls and the rats, okay, a predator and a prey, all right, that relationship we can succinctly represent by, and I want to try using my stylus here, you can succinctly represent that by this matrix equation. And x of k, of course, is denoted by the vector with elements O sub k, the owls in the kth month, and R sub k, the population of rats in the kth month, or the number of rats in the kth month. So how are we going to find the matrix A? Can anybody chat out what should the matrix A be? What's the dimensions of the matrix A? What do you think the dimensions are going to be? So this here, think of this system here. I want to take this system, hold on. I'm going to take this system of equations that models the relationship between owls and rats, and I want to write that as x sub k plus 1. Okay, that would model the number of owls and rats in the k plus first month here. Okay, I want to take that and I want to set it equal to a times x sub k. And here's x sub k right here. Okay, so looking at this system of equations and looking at this matrix equation, can you tell me what A would be? What the matrix A would be? Who can chat it out? Well, first of all, what's the size of the matrix A? Let's start there. What's the size of the matrix A? How many rows, how many columns? Okay, that's right. That's right, Benjamin. And Hung, I think I think she meant the same thing. It's 2 by 2. Okay, 2 by 2 matrix A. And what's A going to equal? If A is a 2 by 2, so you have to be comfortable with this. I want you to be comfortable with this. All right, I need 4 numbers. What would the numbers be? Let's see. Hung, Hung, you're almost right. You're almost right. Almost. Almost. Let's see. So Hung says that we should have hold on, let me put it in black. We should have a 0.5 here and a 0.4 here. Yeah. And a 1.1 here. But then what's going to go here? Is it going to be 0.104? Ah, good, Eleni. That's right. Negative 0.104. And you can see just by matrix multiplication, your knowledge of matrix multiplication, that this matrix A times this vector A sub k is going to equal the vector A sub k plus 1. So now you've identified the matrix A. And you can find then the eigenvectors and eigenvalues. Are there any questions on this? Are there any questions at all? I want you to be comfortable with this. Nafani, how are you feeling with it? Are you feeling good? Good, good. All right. Naima, how about you? You feeling all right? Gavin, how about you? Gavin, you feeling good? Well, now I'm getting a little worried. All right, thank you, Gavin. All right, I was getting a little worried there. All right, hey, I know we all step out to go to the bathroom, you know, but I don't want too many people going to the bathroom. All right, so all right, now we have our matrix A, and we can find the eigenvectors and eigenvalues. And so here's the matrix A. Here it is. And we'll use MATLAB to help us get eigenvectors and eigenvalues. And so the command sim of A will get us nice looking eigenvalues and nice looking eigenvectors, and it'll store them for us. And so given that command, these are your eigenvalues and eigenvectors for the matrix A. Let me give you a moment to catch up here. Okay, while you're okay. You're welcome. You're welcome. Thank you, Natalie. Very good. Very good. So what happens in when you just, for instance, find, well, I want to be careful here. So, you know, MATLAB can give you eigenvectors and eigenvalues. You know, it can give like eigenvectors with decimal entries, or it can give eigenvectors with nicer looking entries. And using this sim command will help get you nicer looking entries. But you don't always really need the nicer looking entries. But for this problem, for the MyMathLab homework, you actually do. It is often desirable to have eigenvectors that are in nice form, because we can interpret those eigenvectors. You know, we can interpret those as well. So, all right. Are there any questions up to here? All right. Just see here. One moment, class. Looking for, yeah, fine. Okay, so now what we're going to do is we're going to write out the formula for the population of owls and rats. Okay, the population of owls and rats after K months, using the formula that we learned already from section 5.6, the iterative formula for x sub k. It turns out then, with these eigenvalues and the corresponding eigenvectors, the iterative formula, I don't know what, hold on, I think I had my page set. The iterative formula is going to be this. So after K months, the population of owls and rats given by the vector x sub k will equal C1 times 0.58 to the kth power times the eigenvector 5, 1, plus C2 times 1.02 to the kth power times the eigenvector 10, 13. So it's a beautiful iterative formula, and it's an absolutely amazing formula because we can now, if we want to, know the evolution of these owls and rats. Okay, for instance, are the populations of owls and rats going to go extinct over time? Well, all we need to do is let k get large. Okay, let k get large. Okay, well, we let k go to infinity to see the evolution of the system, but we note here that when k is large, the population of owls and rats is approximately equal to C2 times 1.02 to the kth power times the eigenvector 10, 13. Oh, well, what's happening here with the first term? What happened to the first term? I don't see it here for k large. It's disappeared. Why? And all right, you're right, Hung. Why does it go to 0 as k increases? What causes this portion to go to 0? In other words, what we're saying here is this term, this vector term, approaches the vector 0, 0. Okay, this means this is approaches 0, 0 as k approaches infinity. I want to know why that is. Why would that be? Let's focus on this 0.58 to the kth power. That's right, Hong and Nafani. That becomes small. 0.58 to the kth power, that goes to 0 as k goes to infinity. That goes to 0. I mean, on your calculator, take 0.5, we're in decimals, take 0.58 and raise it to the 50th power. And you'll see that you get a very small number. Okay, a very small number. It's in scientific notation, like on the TI-84 calculator, but it's very small. I mean, if you take 0.58 times 0.58, okay, what's 0.58 times 0.58 times 0.58 is 0.3364, right? Multiply that by 0.58. You keep going, and you're going to eventually, that's going to go to 0. Okay, are there any questions here before we on that? So in other words, the eigenvector 1.02, well, you know, that's okay. But what do we have to worry about in terms of terms disappearing? What eigenvalues, you know, what eigenvalues would be, I want to say this the right way. What eigenvalues, we have a two by two matrix. Under what conditions would the population of owls and rats go to extinction? This is a general question I'm asking, but like I'm wondering, you know, when would the population of owls and rats go to extinction? That means 0, 0, right? That means no owls, no rats. Under what conditions would the populations of owls and rats, under what conditions would the owls and rats eventually become extinct? In terms of the eigenvalues. Well, Benjamin, I have to think a little bit more on what you're saying there, but I'm focusing really, it's clear these eigenvalues are very important, right? It's clear these eigenvalues are very important. Well, and both terms here, k goes to infinity. Okay, and let's say for instance that we had gotten an eigenvalue. Let's say lambda 1 was equal, you know, lambda 1 was 0.58. And let's say that lambda 2 was equal to 0.79. Hold on, I can write better than that. Hold on. Okay, let's say that lambda 1 is 0.58 and lambda 2 is 0.79. Would that spell trouble for the owl and rat populations? Okay, Justin says yes. In other words, let's say up here, instead of one, let me phrase it another way. I don't really want to erase what I got here, but let me just, gotta be a little careful here. Let's say up here, we had 0.79. I can't get it in good enough. Hold on. Hold on, class. Hold on. Maybe I'll put it in with my stylus. I use the stylus sometimes. Put it in blue. So what I'm saying, if we have C2 times 0.79, gosh darn it, I can't get it good, class. I want to get this right. Let's try it again. C2 times 0.79 to the kth power. Let's say that this were the second term. Well, what does 0.79 to the kth power go to as k goes to infinity, class? What does that go to, that term? Okay, goes to 0. That's right, extinction. So what eigenvalues would cause extinction here? What are the conditions on the eigenvalues that would cause that on both eigenvalues that would cause extinction? Well, I mean, we had lambdas. Well, but remember, hold on. Remember, Nafani, here, like the 1.02 to the kth power, okay, that 1.02, if you raise that to the kth power, that term isn't going to go to 0. 1.02 times 1.02 times 1.02 and so forth, that's gonna go to infinity. There's a key value you have to watch for. That's right, Hung. If the eigenvalues are less than 1, then your populations are going to go to extinction. If all your eigenvalues are less than 1, the population will go to extinction. So if you're doing a study, okay, and you compute eigenvalues, and all the eigenvalues, you know, for your particular iterative vector equation for the populations in the kth month or kth year, if both eigenvalues are less than 1, then then those populations are going to go to extinction, and in that case, you know, policy has to be made so that that doesn't happen. I mean, how do they determine when these populations are endangered? You know, endangered species. How do you know that? How do you know that? Well, you have this kind of analysis, right? And in this case, of course, since one of our eigenvalues is larger than 1, okay, for our owl and rat population, what's that tell you about the owl and rat populations? Are they going to go to extinction? Or are they going to survive? So we had one eigenvalue less than 1, but we have another eigenvalue here greater than 1. So the owl and rat populations, are they going to grow over time, or are they going to go to extinction? Well, let's talk about that. All right. So let's continue here then with what we were, you know, with the problem at hand. So when k is large, okay, because the first term here drops out, okay, goes to 0, 0, then the Allen rat populations can be approximated by the second term. And the second term here does not drop to 0. The second term does not drop to 0 because 1.02 to the kth power does not go to 0 as k gets large. It goes to infinity. Okay, so it's always there. So the Allen rat populations for k large will be approximately equal to C2 times 1.02 to the kth power times the eigenvector 10, 13. Now, that means when k is large, we can also say that in the k plus first month, the Allen rat populations would be approximately equal to C2 times 1.02 to the k plus first power times the eigenvector 10, 13. But look what I can do. I can take 1.02 to the k plus first power and write it as 1.02 times 1.02 to the kth power. I can do that. And when I do that, okay, the C2 times 1.02 to the kth power times 10, 13, well, that's just equal to x sub k up here. Okay, and so this means then eventually the number of owls, I mean, we're saying that x sub k plus 1, the number of owls and rats present in the k plus first month, okay, will eventually be approximately equal to 1.02 times the number of owls and rats in the kth month. So eventually the number of owls and rats grow by a factor of 1.02 each month, or a 2% monthly growth rate. Additionally, for every 10 owls, there will be about 13,000 rats. That's where the eigenvector comes in. Okay, so I want to make sure that you're comfortable with this. I want to do another example with you. Okay, but are there any questions on this? Okay, well let's look at another example here. Okay. Actually, hold on. Let me hold on, class. Hold on. I'm going to stop the recording.